Welcome, Hillsdale College. History of economic thought, and we're going to proceed. We're going to start out today with finishing up the English school, as I mentioned. So this is going to be Edgeworth and Pegu. But we always start out, I was going to see, are there any announcements? Praxis events, CLO? Nope, nothing yet. Well, we'll work on it. So let's go ahead. I want to finish up with the English school, and then we're going to proceed to School of Lausanne and Walras. So we start with Francis Ysidro Edgeworth. Francis Ysidro Edgeworth, F.Y. Edgeworth, he lived 1845. (1926). And he is known for being the inventor of utility functions and indifference curves. He was very mathematical, more so than anybody we've talked about previously, except perhaps Cournot. He's another difficult character. It was said about him, Francis is a nice chap, but beware of Ysidro. Well, he ended up at Oxford University. He taught at a number of schools, ended up at Oxford, and it's said that at Oxford, his lectures were not well attended. He was happy lecturing to a room with 0 people in it. He'd be lecturing, people would get up and leave, and there'd be nobody. He was happy to be filling the board with mathematics. Speaking of nobody in the room, at any rate, I'm following in his footsteps. But he's most important for his book, 1881, Mathematical Psychics. And by this, what he means is a mathematical treatment of the psychology or the mental process of utility maximization. Mathematical Psychics, 1881. Interesting book. Well, in it, he bases this on mechanics and on physics. He argues that the Marshallians, he's something of a Marshallian himself, but he argues the Marshallians have been seduced by the zigzag windings of the flowery path of literature. What it all is maximization. It can be handled with mathematics. And so he comes up with the idea of utility functions. Utility functions are, of course, implicit in the work of William Stanley Jevons, but they're formally developed by Edgeworth. And that the utility function is a mathematical representation of the preferences of an individual. So it applies to the individual. It's a way of representing them. And it's got some use to it. So I'm going to give you an example here. Suppose we only have 2 goods. I'll put utility for a person, me, my initials. Utility of good x and good y is equal to some function. And I'll give an example of such a function, but it would give us a level of utility, some number, a way of measuring how much utility they're getting from different combinations of good x and good y. And of course, you could put more than 2 goods into this, have as many as you want, and it would be different for different individuals. Your utility function is probably not the same as mine. Unless we all have identical preference rankings, the functions will be different. Jevons' total utility concept implies the existence of such a function. Jevons has the final degree of utility. That's just marginal utility, the rate of change of this. So the marginal utility is simply the change in the utility of x and y for a change in, say, good x. Or good y, whichever one it is. Mathematically, in terms of calculus, that could be represented as the partial derivative of this with respect to this. And of course, if you haven't had calculus, that's just the little turned d is the symbol for the rate of change for a given variable. So let me give you just a quick example of one that you might see sometimes, and that is the Cobb-Douglas utility function. named for the two American economists who had developed this one. It's very easy to work with and has properties that are somewhat nice. And so Cobb-Douglas utility is utility equals, this is an example of one, x to the 1/2, y to the 1/2. So notice it's multiplicative. It's not additive. It's multiplicative. And the form will make a difference. So what's the marginal utility here? Well, the marginal utility of x would be equal to du dx. And if you know what that is, it looks like, if you know calculus, 1/2 x to the minus 1/2 y to the 1/2. Marginal utility is positive. Okay, great. What else can we see from that? So that's necessarily greater than 0 if you're consuming some x and some y. We can also look at the second derivative, and we see that d squared u dx squared is equal to, it looks like, minus 1/4 x to the minus 3/2 y to the 1/2. That's negative. That shows diminishing marginal utility. And so that's thought to be a nice property because that's less than 0. Positive marginal utility, but it's diminishing. And that's why this one is often used. Great. Well, here's what Edgeworth points out. That utility function applies to individuals, not groups. So if we go back and think of what Jevons had done with his trading bodies formulation, that wasn't quite the correct formulation of equilibrium. That wasn't the way to show it because it is an individual matter. What Edgeworth is able to show in mathematical psychics is that the actual statement of a trading equilibrium would be that the marginal utility of good x for person 1 and the marginal utility of y for person 1 is equal to the marginal utility of x, marginal utility of y for person 2 equals ... all the way up to however many, if we have n people, marginal utility of x, marginal utility of y for the nth person, and that must be equal to price of x over price of y. So effectively, that's what the correct statement of equilibrium is, and the correct statement of how the marginal utility is related to price that Jevons has worked on. Great. Edgeworth also shows that if you have only two people, the equilibrium price ratio is probably not unique. In fact, it's not unique. So we'll continue that when we get to Pareto under the School of Lausanne. Great. Well, let's move then to indifference curves. What are indifference curves? And this builds on this concept of the utility function. So the indifference curve is a way of graphing or representing preferences. Okay, let's assume that we have divisible goods, in fact, infinitely divisible goods. So something like water, you can have different quantities. It's not like you can split up a bar of gold into little small pieces or a unit of water into almost infinitely divisible amounts. So we're not talking about a car where half of a car isn't really a car. So this means, though, that we can think of this as being a continuous function, and that's what we'll do. And so we'll stay with our Cobb-Douglas example. The utility, imagine this, utility of x, let's do it this way, the utility is equal to x to the 1/2, y to the 1/2 for me. There's my consumption of the amount of xylophones that I have and the number of yaks that I have, but we'll think of them as being continuous in some way. Great. Well, for some fixed amount of x and fixed amount of y, that will be equal to c. It's a constant. It's just the amount of utility that I'm getting for fixed amounts. So we can rewrite this as, doing the math, y is equal to, u squared over x. So all I've done is squared both sides, and then I've divided both sides by x to get this. Great. So for a given level of utility, for example, if the utility is equal to 5, well, I can graph this. I would then graph y equals 25 over x. Or, if instead we're talking about a different level of utility, we'd have, if u equals 10, we would simply graph y equals 100 over x. Great. And what will that give us? That will give us, the graph will show all the different baskets of goods that will give me exactly 5 units of utility. This would give me all the baskets of goods that would give me exactly 10 units of utility. Let's do that. If you know anything about what the graph of those things would look like, we end up with the following. Here's y, x, Steele's preferences, so we know what space we are working in and what it means, and that would be a graph like this. U equals 5 and u equals 10. And what that tells us, for example, we'd have points such as something like the utility is equal to 5, so we'd have a point like that, a point like that, a point like that, a point like that. That amount, x naught, y naught, that basket gives me the same amount of utility as this one, x1, y1. And that's true for any other basket along there. They all give the same amount of utility. And similarly, there we have it for a higher level of utility. So we could say, well, we could say x naught and y3, etc. Those would give more, that basket, anything along there gives more than the basket along there. Great. All right, so we know now what those are. And using this, we are going to be able to develop a method of showing how we can get multiple equilibria. Pareto is going to take this approach and turn it into what is called the Edgeworth box. Pareto invented that, not Edgeworth. So great, that's good. That's pretty much all we need to cover with respect to Edgeworth, but he's famous for this. And so great. Let's proceed to our next member of the English school. We'll finish that up. And this will be quick because we will do A.C. Pigou. Alfred Cecil Pegu. Let's see, Pegu, A.C. Pegu. And Pegu lived 1887 to 1959. He was Marshall's replacement. He was Marshall's successor at Cambridge, a student of Marshall. But when Marshall retired, he took over as head of the Cambridge School. He was a dedicated Marshallian. He was also a mountaineer. He actually hiked with Friedrich Hayek. He was a pacifist. He opposed intervention in World War I, and he began as quite a laissez-faire advocate. But as his career went on, he became increasingly interventionist. And in the process, he develops the theory of externalities and market failure. If you remember going back to Alfred Marshall, Marshall talked about external economies and external diseconomies. An external economy is the kind of thing that gave us the downward sloping supply curve for the industry, the decreasing cost industry, with things like the trade journal effect. Well, Marshall also had the external cost, and that was things such as the factor price effect, where all of the firms, even if you had otherwise a constant cost industry, they all bid up the price of a necessary input, and so we end up with the increasing cost industry. Well, Pigou takes the idea of external costs and external benefits and develops the notion of externalities. These are, by his definition, costs and benefits that are not taken into account by decision makers, and they are imposed on others. Now, later on, a number of economists, Ronald Coase, Stephen Chung, Charles Steele, will say, hang on, this changes the definition of cost. But we'll get to that. James Buchanan does as well. But here's the kind of example that Pegu suggests. He says, think about the production of steel. So this is the theory, Pegu's theory of externalities. And we're going to have steel production. I have to be careful not to put the E on the end there. It's a habit, good habit to get into. And so we'll put dollars per unit on this axis, price, for example, costs, and quantity on this axis. Great. All right, this is a simple graph. Everyone, I think, already knows it. But there's our demand curve. This is the market for steel. I can't help it. We're going to put we got the demand curve here, and we have the marginal cost for the industry. Marginal cost for the industry, and that's equal to the supply curve. Great, so we have an increasing cost industry here. Marginal cost to the steel firms. That's what they bear. And of course, we know that the equilibrium point will be right here. There's the quantity Q star of steel, and there is the price of steel on the market, whatever that happens to be. And then Pegu says, aha, but what about what about the problem of externalities? And so we'll take a look at that. Every time they produce a unit of steel, they also produce a unit of smoke, and it lands on people's houses, does damage in some way or another. And let's assume that that damage is constant. We'll just have D is the amount of damage. We'll assume that for every unit of steel, it puts out, I don't know, $10 of damage. Doesn't particularly matter, but we'll have it be constant just to make it easy to draw. Great. So what I'm doing now is adding, as Pegu does. We have marginal cost here. There's the marginal cost for the industry plus that marginal damage. There's our marginal damage. Great. And of course, this is the marginal valuation of the steel to the buyers, to the consumers. But now we've taken into account the damage. And here's the story that Pegu tells. He says, there has been a divergence between private cost and social cost. This is the private cost borne by the firms, but there's the social cost that takes into account the damage done to homes, consumers, whoever's suffering from the smoke. And so we've got the amount of damage in our story right there. Great. So what's the solution? Pollution is a problem. So of course, stop production, right? And of course, Pegu's answer is no, and that's not right at all. Because this stuff is valuable. We just want to make sure that for these last units that are produced, the value that people attach to them is less than the cost, the full social cost. And so we don't want to produce those. That's wasteful, bad allocation of resources. Pegu says what we should do is strive to achieve the socially optimal amount of production, which would be taking the damage into account. You still want to produce some because it is valuable. At this point, at that higher price, we are taking the damage into account, and still those first units are worth more than it cost to produce them, even counting the damage. Well, says Pegu, the divergence between private costs and social costs means the free market is suboptimal, it's market failure. And the solution is regulation, or a Pegovia. You could put on a tax per unit, you could have a regulation, you could put liability laws, other kinds of government interventions. And so Pegu makes this case for market failure, government correction. When we get to the next, there's another Englishman that I want to talk about, and that will be Ronald Coase. I won't talk about him today, other than to say that Ronald Coase is highly critical of this analysis, and he says Pegu's analysis is all wrong. It's confused, it's fallacious, it is misleading, and it has sent microeconomics down a wrong path. This is not the Coase theorem that he will talk about. It's something different, and so we are going to continue with that. But that's about all I need to say about the English school. We'll say a bit about John Maynard Keynes, who was also a student of Marshall, but we'll hold that until we get to macroeconomics. And so, on that happy note, I guess it's happy, we're gonna stop this lecture, and when we come back, we will talk about the School of Lausanne.